When working with a 1200 kilowatts, 13.8 kilovolts, 3-phase, 4-wire emergency generator with neutral grounded through resistance, there are specific wiring and grounding practices to follow. Firstly, concerning carrying neutral and ground cables from the generator to the 15 kilovolts breaker, you should carry all 3-phase cables, the grounded neutral cable, and a separate ground wire. It is essential to run all these conductors together to ensure proper operation and safety. Secondly, regarding bonding the generator neutral must be bonded to the first 15 kilovolts breaker enclosure. This bonding provides a low impedance path for fault current, which is crucial for the correct operation of protective devices. Thirdly, you should continue carrying the neutral or grounded conductor all the way to the 480 volts breaker enclosure. This continuous neutral connection is necessary because the 480 volts system is derived from the 13.8 kilovolts to 480 volts step-down transformer, and the neutral serves as the reference point for the phase voltages. Now let's discuss carrying neutrals in the low-side transformer conduits. You should not carry a neutral in each conduit in the low side of the transformer. The transformer's secondary has a grounded Y configuration with a single neutral conductor that is shared by all 3 phases. The single neutral point is established at the transformer secondary, and this neutral is then distributed to the downstream equipment. To elaborate on these points, let's delve into the reasons behind these practices. The presence of a dedicated ground wire alongside the phase and neutral conductors is essential for safety. This ground wire provides a low impedance path for fault currents, which helps to quickly trip circuit breakers or blow fuses in the event of a ground fault. Without a dedicated ground wire, the fault current might have to travel through unintended paths, potentially causing damage to equipment or posing a safety hazard to personnel. The bonding of the generator neutral to the 15 kilovolts breaker enclosure is another critical aspect of the grounding system. This bond ensures that the breaker enclosure is at the same potential as the neutral, which helps to prevent voltage differences that could lead to electric shock hazards. The continuous neutral connection from the generator to the 480 volts breaker enclosure is necessary for maintaining a stable voltage reference in the 480 volt system. The neutral conductor provides a common return path for the current flowing in each of the 3 phases. Without a continuous neutral connection, the phase voltages could become unbalanced, leading to equipment malfunction or damage. The practice of using a single neutral conductor on the low side of the transformer is based on the principle that the neutral point is established at the transformer secondary. Since the transformer has a grounded Y configuration, the neutral point is the common connection point for the 3-phase windings. This single neutral point serves as the reference for all 3 phases, and it is from this point that the neutral conductor is distributed to the downstream equipment. Carrying a separate neutral conductor in each conduit would be redundant and unnecessary. In summary, the correct wiring and grounding practices for a 1200 kilowatts emergency generator involve running all 3-phase cables, the grounded neutral cable, and a separate ground wire from the generator to the 15 kilovolts breaker. The generator neutral should be bonded to the 15 kilovolts breaker enclosure. The neutral should be carried continuously to the 480 volts breaker enclosure. And, on the low side of the transformer, a single neutral conductor should be used to serve all 3 phases. Now let's consider the specific components and considerations for this setup. The 15 kilovolts breaker is a crucial part of the system, providing overcurrent protection and isolation for the generator. The breaker should be sized appropriately for the generator's output current and should have the correct interrupting capacity for the system. The 15 kilovolts to 480 volts step-down transformer is responsible for converting the generator's output voltage to a level suitable for use by the facility's electrical equipment. The transformer should be sized appropriately for the load and should have the correct impedance to limit fault currents. The 480 volts breaker provides overcurrent protection for the downstream equipment. This breaker should also be sized appropriately for the load and should have the correct interrupting capacity. When selecting conductors for the generator wiring, it is important to consider the ampacity of the conductors, the voltage drop, and the environmental conditions. The conductors should be sized according to the National Electrical Code, or neck to ensure that they can safely carry the generator's output current. The voltage drop should be kept to a minimum to ensure that the equipment receives the correct voltage. The conductors should also be suitable for the environmental conditions in which they will be installed, such as temperature, moisture, and exposure to chemicals. Grounding is a critical aspect of the generator system, and it is important to follow the NEC guidelines for grounding and bonding. The grounding system should provide a low impedance path for fault currents to ensure that protective devices operate correctly. The grounding system should also minimize the risk of electric shock hazards. Bonding involves connecting all metal parts of the electrical system together to create a common ground potential. This helps to prevent voltage differences that could lead to electric shock hazards. Bonding should be performed according to the NEC guidelines. In addition to the wiring and grounding considerations, there are also several other factors to consider when installing a generator system. These factors include the location of the generator, the ventilation requirements, the noise levels, and the fuel supply. The generator should be located in a well-ventilated area to prevent overheating. The noise level should be kept to a minimum to avoid disturbing neighbors. The fuel supply should be reliable and adequate for the generator's operating time. The neutral grounding resistor, or NGR, is a crucial component in the generator grounding system. Its purpose is to limit the ground fault current to a safe level, typically a few amps, while still allowing protective devices to detect and clear the fault. Without an NGR, the ground fault current could be very high, potentially causing damage to equipment and posing a safety hazard. The value of the NGR is typically selected to limit the ground fault current to a level that is high enough to reliably trip protective devices but low enough to prevent excessive damage. The NGR should be sized to withstand the continuous current that will flow during a ground fault. When installing the NGR, it is important to follow the manufacturer's instructions and to ensure that the connections are tight and secure. The NGR should also be protected from the elements to prevent corrosion. The generator control system is responsible for starting, stopping, and monitoring the generator. The control system should be reliable and easy to use. It should also provide information on the generator's operating parameters such as voltage, current, frequency, and power. The control system may also include features such as automatic transfer switching, which allows the generator to automatically start and supply power to the load in the event of a power outage. The automatic transfer switch, or ATS, is a device that automatically switches the load from the normal power source to the generator power source in the event of a power outage. The ATS should be reliable and fast-acting to minimize the interruption of power to the load. The ATS should also be sized appropriately for the loader and should have the correct voltage and current ratings. When selecting an ATS, it is important to consider the type of load that will be connected to the generator. Some loads, such as motors, may require a different type of ATS than other loads, such as lighting. The NEC provides detailed requirements for generator installations, including the sizing of conductors, the grounding of the system, and the installation of overcurrent protection devices. It is important to follow the NEC requirements to ensure that the generator system is safe and reliable. Some relevant NEC sections include Article 445, which covers generators, Article 250, which covers grounding and bonding, and Article 700, which covers emergency systems. In addition to the NEC, there may also be local codes and regulations that apply to generator installations. It is important to check with the local authorities to determine the specific requirements for your area. Regular maintenance is essential for ensuring the reliable operation of the generator system. Maintenance should include periodic inspections, testing, and cleaning. The generator should also be exercised regularly to ensure that it is ready to operate in the event of a power outage. The maintenance schedule should be based on the manufacturer's recommendations and the specific operating conditions. When performing maintenance on the generator, it is important to follow all safety precautions. The generator should be de-energized and locked out before performing any work. Personal protective equipment, or PPE, such as gloves, safety glasses, and hearing protection, should be worn. Here are some additional considerations for the 13.8 kV system. Working with 13.8 kilovolts requires specialized knowledge and equipment. Only qualified personnel should perform work on this system. Proper safety procedures must be followed to prevent electric shock hazards. High voltage equipment, such as switchgear and transformers, requires regular inspection and maintenance to ensure reliable operation. Proper insulation and clearances must be maintained to prevent flashovers and other electrical faults. Surge protection devices should be installed to protect the equipment from voltage surges caused by lightning or other events. Coordination studies should be performed to ensure that the overcurrent protection devices are properly coordinated to minimize the extent of any outages. Arc flash studies should be performed to determine the potential arc flash hazards and to select appropriate PPE. Now let's talk about some best practices for generator installations. Firstly, always follow the manufacturer's instructions and the NEC requirement. Secondly, use qualified personnel for all work on the generator system. Thirdly, perform regular maintenance and testing. Fourthly, keep accurate records of all maintenance and repairs. Fifthly, provide adequate ventilation for the generator. Sixthly, minimize noise levels. Seventhly, ensure a reliable fuel supply. Eighthly, install proper grounding and bonding. Ninthly, use surge protection devices. Tenthly, coordinate overcurrent protection devices. By following these best practices, you can ensure that your generator system is safe, reliable, and compliant with all applicable codes and regulations. Another critical aspect is proper labeling and signage. All components of the generator system should be clearly labeled to identify their function and voltage. Warning signs should be posted to alert personnel to potential hazards. Emergency shutdown procedures should be clearly displayed. Single-line diagrams should be available to show the configuration of the system. Proper documentation is essential for the safe and efficient operation of the generator system. This documentation should include the manufacturer's instructions, the NEC requirements, the local codes and regulations, the maintenance schedule, the test results, and the repair records. This documentation should be kept in a safe and accessible location. In conclusion, installing and maintaining a 1200 kilowatts emergency generator requires careful attention to detail and a thorough understanding of electrical principles. By following the guidelines outlined in this narration, you can ensure that your generator system is safe, reliable, and compliant with all applicable codes and regulations. The information presented here is intended for general guidance only and should not be considered a substitute for professional engineering advice. Always consult with a qualified electrical engineer or contractor before performing any work on a generator system. Understanding the specific requirements of your installation and adhering to all applicable codes and regulations is crucial for ensuring the safety and reliability of your emergency power system. Remember that safety is paramount when working with electrical systems. Always follow proper safety procedures and use appropriate personal protective equipment. If you are not qualified to perform electrical work, hire a qualified professional. A well-designed and properly maintained generator system can provide a valuable source of backup power during emergencies, ensuring the continuity of critical operations. From properly running the neutral to proper maintenance, you're on the right path.